Hello, my name is Mikhail. I'm an engineer on the environments team. This is a demo of an idea that I call GitLab Flow. So here's the product ideas that I believe are worth pursuing. Automation is key to higher productivity and efficiency. In the end, every business that is our customer wants to solve their problems in the DevOps domain. And automating is a huge part of solving those problems. So the idea is that GitLab users automate those tasks across the whole DevSecOps domain. And GitLab should be at the center of that. It should be the platform that allows users to manipulate DevOps domain objects that are in GitLab, but also it should allow to work with external systems via the APIs that they provide. Let's look at some user stories that I think make sense, and as examples of what I mean. This is a simple one. When a new issue is created, it should be labeled in a certain way. Labels should be adjusted if set incorrectly. I think we have some projects that do that across the whole GitLab org group, top-level group, and probably GitLab.com as well. So it's an obvious use case of automation. Use case where automation makes sense. Another one is a more complex one. When a new release is published and we are not in a production changelog, kick off a deployment to Canary production. Let's say we don't have other environments, but there may be. Then let Canary run for 3 hours. While it's running, if there is an alert generated by our observability stack for this environment, for the Canary part of it, roll back the deployment. So otherwise, if there was no alerts, proceed deploying that release to production, and then keep listening for alerts for another 3 hours from the whole production, both Canary part and not Canary. And then if there is a problem, if there is a signal, rollback. Then if actually there is a changelog, wait for it to be lifted and then proceed with the above process. And then another complication to make it more interesting is that is if a new release is published while we are waiting for PCO to be lifted, then we should finish this workflow because another workflow is started for that new release that is published. And then I think this is a good example because deployments are a business process. They're quite important, right? So they are usually, hopefully, automated and should progress reliably. They shouldn't fail in some intermediate indeterminate state if a VM crashes or pod fails that is executing that process, executing that logic for any reason. Yeah, it should just proceed with what it's doing. And another example is in interaction with external systems. Let's say we want to have a workflow when that checks some metadata on an uploaded file that in a Google Cloud bucket or anything like that. This is just an example. So yeah, it's an interaction between some external system and the automation inside of GitLab. So how can we address such use cases, such needs? And typically, people automate things by writing shell scripts because they are quite versatile. You can interact with like anything basically because it's code that runs and can make external API calls and read files and so on. But if you have ever tried to write a shell script, you probably know how notoriously difficult it is to get it right. Or the cryptic syntax is a huge barrier, I think, and then they are not very portable because depending on the system, they may not work the same way, or even the version of the shell interpreter itself. And yeah, they're low level and often cannot actually run for that long enough, because yeah, if the machine stops, then usually it's not safe to just restart the script. It will not continue from where it stopped unless it was designed to work that way. But most of the scripts are not designed to work that way, and it's actually difficult to design a program to work that way, because you would need to reconstruct all the state of the program, all the variables, and where it's actually executing at the moment, and so on. It's not how shell scripts work. So yeah, and usually nobody tests shell scripts. Like, there are no testing frameworks for shell scripts, and you just run it to see if it works in production. So there is a better approach, and it's to use a workflow engine as an underlying mechanism of durable execution. And Temporal is one such workflow engine. It's a platform, an SDK, or a framework to durably run workflow definitions. And it was built by folks who have lots of experience, who built all these services and frameworks that are widely, I would say, widely successful and widely used. And kind of Temporal is the next iteration on top of Uber Cadence, which was the latest from them before that. And it's a company that provides Temporal as a service, or you can run yourself, self-manage it. Let's see how it works. They actually have a pretty good explanation here. So there are separate components. There's a client. So this is a program, an application that makes a call via the Temporal client to start a workflow. In this case, a workflow does a money transfer. Yeah, workflow is what defines the business process, the business logic as code. So here is money transfer with some input, some parameters. So from account to account and how much in this example. Then the second component of client, second component is the server. Server is the Temporal server, and its job is to track the state of the workflow in a database and coordinate the execution of activities. Activity is a task to actually do something on the outside world. So workflows need to be deterministic, and then they can't do anything by themselves. They call activities to actually do something. So in this case, the Temporal server in the event history records that a workflow execution has started, and that the task to the workflow task has been scheduled. Then there is a worker, the third component, and it pulls the task to execute the workflow logic. So yeah, it's a function that is defined in the worker application. Worker and client can be the same application, but they don't have to be the same application. So first part of that money transfer workflow is to execute an activity to withdraw the amount of money that is given in the input parameter. So input payment details is just given to that activity, withdraw activity, and then it produces a string. That activity produces a string. Just as an example, it can produce any value of any type. So the temporal server records that activity withdraw has been scheduled, and then the worker, which may be actually the same worker or another worker, pulls the task to, well, I think they call it commands, to execute this activity withdraw, and has the data that contains the information about how much to withdraw, and it contains the account number. So it talks to a bank to withdraw this amount of money from this account, and then it returns the confirmation as a string. Then when this is done, temporal server records that the activity is done, it has completed, withdraw activity is complete now, and then it schedules the workflow execution again. Again, the worker picks up that and continues the workflow function. How that actually works, we'll talk about this later. This continuous bit. Then continuation of that workflow. So we have withdrawn some money, we need to deposit the money. So we have another activity that also is given the input parameters to deposit the money into the destination bank account. So same thing, activity is scheduled and then started when worker picks it up. And then this is the deposit activity, bank deposit, target account, and how much. And that's kind of obvious. It returns confirmation as a string as well. And then this is, yeah, this is invoked, this is executed. Then let's say in this example, talking to the bank API fails. If this is, yeah, this is talking to the bank API in this example. So activity will be retried with some retry policy. And let's say the next time it is retried, it succeeds, and the money is finally in the destination account, hopefully. So this is recorded in the history as well, that the deposit activity is done, is complete, has been completed. And then the workflow task is scheduled again, and then it started. So the worker continues the workflow function, and it prints the outputs from the first and the second activities, here just as a string in this example. And yeah, then this is the client application that invoked the workflow here, the money transfer workflow. It waited for the workflow to finish, and it got the result back, and then it just prints the result here. And the result is just this string, transfer complete, transaction ID, blah, blah, blah. And yeah, and event history contains the record of all the events and that workflow execution has completed. Yep, this is how it works. So there's, to recap, there is a client, there is a temporal server, and then there is a worker. Client and worker can be the same program, but can also be different programs. So there are workflows and activities. Workflows need to be, yeah, in the technical words, workflow state. So state of the workflow program or function is reconstructed when the workflow is executed using the event history that is persisted in the database by the temporal server. And this is basically event sourcing. You reconstruct some state based on the history of what happened. And then, yeah, using the deterministic workflow code. It must be deterministic because if you have a history of events and you have a non-deterministic program that is fed those events, different times you run it with those same events, you have a different state. and then program behaves differently from one invocation to another invocation. You don't want your bank account to be, non-deterministically deposited or not deposited with the money. And activities are just side effects, basically, that the workflow program uses to actually communicate with the outside world. And they must be idempotent so that if an activity fails, it can be retried. And once it succeeds, the fact that it has succeeded is recorded in the database, and it will not be invoked another time unless required by the workflow, of course. So the result of the activity will be memorized or cached. Maybe there are more familiar words, and reused later during the replay, replay of the event stream, basically. So yeah, well, this is what I just explained. There are SDKs that Temporal provides for these languages, and I think I haven't looked at other SDKs, but the server is in Go, so I assume the Go SDK is the most advanced SDK as well. It's really well written, and there's so much documentation. So, as I said, about the event stream and determinism, if you look at this is the event history. So the workflow function, where is it? This is a piece of the workflow function. No, wait. Yes, this is the piece. So it basically is executed every time you make progress. But instead of actually executing an activity, the persisted state, persisted result of that activity invocation, if that has happened already, is used instead. And it just proceeds to continue, to run, to make further progress. So this is explicitly called out here in the documentation that workflow function must be deterministic. And I'm talking about this so much because it's really important. And okay, so this leads us to Starlark, and let me explain what it is. So Starlark is a programming language that is a subset of Python. It was invented, I could say probably, by Google as a way to define builds for the Bazel build system, which is what they use to build the internal monorepo. It's very efficient, and the requirement for the definition, build definition language, was that it must be deterministic, otherwise you cannot cache the results, basically. And if you can't cache, then you can't reuse the results, and then that means you have to rebuild everything from scratch, which is what you want to not do, right? To be fast. Yeah. So these are the design principles of Starlark. So executing the same code twice will give the same results, which is exactly what is required by Temporal for workflows, for workflow definition code. Hermetic execution, it can't do anything. The language itself doesn't allow you to do anything with outside the world, unless the application that is the host of the Starlark interpreter gives the Starlark code means to interact with the outside world. Then it's designed for parallel evaluation. It is guaranteed to be thread safe, but at the same time, not at the expense of parallel execution, parallel evaluation. So they can be more loaded, and modules are pieces of Starlark code. They can be loaded and run concurrently, because the shared data becomes immutable, so you cannot have data races. Then it's simple because it's a subset of Python. It doesn't have a lot of things that Python has, and that makes it impossible to write complex code, basically. And they have removed lots of pitfalls from the language. So yeah, it's Python basically, and well, it's not Python, but syntactically it's valid Python. But yeah, it's not Python because it doesn't have all the Python features. So yeah, but anyone who can read Python will be able to read Starlark. Same semantics, same syntax. And the third thing here is cloud events. So if you want to automate something that is triggered by an event, then that event needs to be represented in the system somehow. And cloud events is a specification that is an industry kind of standard to describe events in a vendor agnostic way. There are quite a few vendors here in an alphabetic order that have adopted this specification. And there is also Google Cloud. So that's where the bucket example comes from. Yeah, lots of names here, and there's probably not an exhaustive list. So this is the third component. So basically, we have a demo of a mix of those three components: temporal, Starlark, and cloud events, all integrated into GitLab as a way to automate tasks across the whole DevSecOps domain. Yep, so let's see a demo. This is a demo that will be in several kind of steps, increasing complexity of the task that we are trying to automate. So the first thing is, let's imagine the simplest possible thing. When you create an issue, it needs to have certain labels in there in a certain project. And I have this is JDK running locally, my branch plus Kubernetes agent server, also on the branch that has this functionality. Most of the code is in the Kubernetes agent server. We don't need any agents for this. It's just the server, no agents. And this is the example program that uses Starlark to program a workflow. So in Starlark, you cannot refer to identifiers that haven't been defined yet, unlike in Python. So you kind of have to read the program from bottom up, because things below refer to things defined before, above. So things below go up. So this is how you bind a handler, this function on event on new issue, to an event type in let me show you this in cloud events. This is the proto definition of a cloud event. Events are defined, or not defined. Events have types, so it's like a type in a programming language. Different events are of different type, and type is just a string. And then the event payload can be bytes, a string, and a protobuf encoded payload. So in this demo, I use protobuf encoded data. Well, we'll see that later. So the type is new issue, and then this is the handler that needs to be invoked. This is how you bind the handler to an event type. You can have 0 or more event handlers for the same event type. Here I just have one handler for this event type. And this is the definition. So this is the event data in the cloud event format. This is the kind of workflow object. So it's like a toolbox of things that you can use to interact with the outside world. So on new event, we want to get the information about this issue. So proto data, issue, ID of that issue. And this is the definition of the, so new issue event has an issue in there, and an issue is this message has an ID and it belongs to a project has an ID and the full path. This is just the payload of the event itself. So yeah, we get the ID of the issue. Oh, sorry, this is the ID of the issue. We call that get issue function. That gives us the, so this goes to the GitLab API, fetches the issue, parses the JSON. This is the issue definition from the GitLab API. Then we turn the labels on that issue into a set, in a mathematical sense, a set of strings. And then we check that the required labels that are here, it's a set of two labels, that if they are not a subset of the actual labels, so some labels are missing, we construct a new set of labels. And the new set is a union of the existing labels and the required labels. And we update the issue with new labels. Actually, see that there's a typo. So this is update issue. That's called edit issue because I renamed it. I forgot to update the example. That single page editor, I love it. So yeah, this is basically, this is the whole logic of the workflow. That's pretty high level, right? It gets the issue, checks the labels, fixes the labels if they're not okay. And these are kind of lower level plumbing functions. Get issue, just an HTTP call, and that is using that kind of toolbox to make an HTTP call. The URL is constructed here, GitLab URL here, and issue ID here, and some headers. And then we check the status that it's 200 basically, just a comparison. Fail if it's not. Check the content type that we're expecting application JSON. Fail if it's something else. And then we decode the string as the JSON body and return that JSON as a Python dictionary, if it's an object, or a string if it's a JSON string or whatever. But it should be an object, so a dictionary. And yeah, this is pretty straightforward. As you can see, I'm using my personal access token here. And yeah, more on the authentication later. But let's see if this even works. So this is Flow demo project, .gitlab flow py. I used py because it gives me syntax highlighting from Python, which is what we need here. This is the same project, root flow demo, and yeah, let's create an issue. Last one. Oh, I should also say that here I have the server running, Kubernetes agent server, and here I have the temporal server running and GDK. So yeah, test one, no labels, create issue. You see it's done something even before the UI renders, and labels are there already immediately. Okay, this is pretty cool. It worked. Temporal server, which I'm running here. This is a development server. It's trivial to install and run. It's just a binary. You run it and it just runs and gives you the API endpoint. Yeah, it doesn't, like if you click, it doesn't actually refresh. It's need to refresh the page. So there are three completed workflow executions. This is when event happens. This workflow type is invoked, which is to download the file, run it. Then this workflow starts child workflow. I think it's a bug that it says it's pending because, yeah, and this is a bug that it says it's running because the actual child workflow is run event handler. This is actually what runs our event handler function. So there is a top level workflow that runs the whole thing, discovers what it should run, and then finds if it has a handler for this type of event that has happened. And then it starts a new workflow for each handler, independent workflow, as a child workflow of this top level workflow. And this is the run event handler workflow. And it has completed already. Yeah, it refers to that parent. And you can see what happened here. It did an HTTP activity, got this is the payload. Sorry, this is the result of the activity. It talked to the API and got all the various bits and pieces of HTTP response, and then this is another activity, HTTP do activity, when it made the request to add the labels. No, this is actually a response. Yeah, response from that request to add labels. Yeah, there should be information about the request. Yeah, this is the input. Yes, this is the response. This is a input to the activity. So make a put call to this URL with these labels and blah, 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 blah. Yeah. So this is rendered and that is hidden. Okay. It's a bit confusing, but it's okay. So yeah, this is the UI of the server that lets you see what's happening. And yeah, this is the first simple iteration of the demo, but this is pretty simple, obvious, right? Let's do something more interesting. First of all, this is kind of, this stuff is kind of plumbing, right? It probably doesn't belong in this file where we want to know this as well. We just want to see business logic. So let's extract it and move it to a separate file to not be in the way. Actually, let's just move it to a different project. So this is a root flow demo. And this is, I already created a separate project, flow library. And this is the library file, library Python. It contains those edit, get issue, edit issue, create issue note to leave a comment, and these helper functions. So we can just replace this with a reference to that to load the library. And prepare it here and when you copy from the presentation from Google Slides, it adds spaces. I didn't know that. Okay, let's only copy. It will be interesting. Let's only copy this part then. Okay, let's copy everything. Demo is not going according to the plan. Okay, but essentially this is the reference to the other project, and we call that other project lib, and we load from lib file libby, and we load symbols get issue and edit issue that we need in this workflow. Yeah, so we removed all the plumbing into a library, and now we only have business logic here, including this variable. I think this is really clean, 20 lines basically. Okay, let's close this and open a new issue. Test 2. Again, this failed to load. There must be a typo because I copied it. Failed to overflow by line 15. Yep, indentation is wrong. Yeah, okay, I'll be. Oh, it's a. So it's using tabs or something. It should be using spaces. Yeah, that's not gonna work. That's not what I planned to show. um, that's, I don't know, replace all the tabs with spaces manually. In the meantime, it keeps trying in the background, as you see. Let's see if this works. No, this will complicate everything, make it slower. Sorry. So should it still what? It succeeded. Okay, maybe there are only some. Okay, no, tabs are okay. So I have incorrect indentation somewhere still, which I fixed. I think this was not okay. But now it works. Let's try again. But yeah, this succeeded eventually, as you see. Let's do a test 3. Yep, it works. Okay, so this is kind of, you can say this is not that interesting, right? Okay, you have extracted the library. What's it's just this the callback that does something. Let's make it more interesting. And I have, let's see if this works, or if there is a typo of some sort again somewhere. No. Let's see. Let's hope this works. Yeah. So what we've done here is we added a loop around this logic, right? And added a slip, a delay. Otherwise, it's the same. Let's hope there are no typos here. Okay, we don't need this anymore. Let's start. Open the fourth issue. Test 4. No, it works. Okay. Cool. So we can see something is happening there, and we can also go to the workflow server and look at, there's a workflow running, and hopefully enforcing that there are labels on the issue. Yeah, so every 5 seconds it checks, and if labels are not okay, it puts them back. I think that's cool. But yeah, you can say that this is still not that interesting because I mean, just a scheduled thing that does something or something like that, or a loop, a program running constantly. But what's interesting is that this is a real workflow. It's executing in a durable way. So I have stopped the server, the worker. I haven't stopped temporal because, as I said, it's a development server, so it doesn't persist the state anywhere, only in memory. So if I stop it, it will lose all the state. But normally it persists it in the Postgres database. So worker is stopped. If I remove the label, nothing will be fixed because the worker is not running. So the way this the events are delivered is the Rails monolith schedules a sidekick execution that sends a hook to CAS. Now CAS is not running, so sidekick is attempting to notify CAS, and CAS would start the workflow. No, that's for a new issue, and for this script, the workflow is already running, so we are just kind of not waking up from the sleep because there's no worker. So activity to resume from sleep to do something else, to proceed with the script, is scheduled. We can probably see it here. Yeah, timed out. But there's no worker. Let's start it. So yeah, it can't continue because there's no worker. We have started it, and oh yeah, the label is back. Yeah. So yeah, it continues working when it's restarted. We didn't lose the fact that there is a business process that enforces labels, that runs continuously. Even though we have stopped the actual executor of that business process, it still proceeds to do what it needs to do after the worker is restarted. Okay, let's make it even more interesting. Okay, if I kind of close the issue, the workflow is still running, right? Because nothing canceled the workflow. Yeah, the label is back. See, it's still running. So yeah, I have to go and cancel it, otherwise it will be running forever. Cancel. So let's fix that, because we don't want to have the, let's say our business process doesn't require to fix labels on issues that are closed, and we can just cancel the workflow once the issue is closed. And to do that, I have prepared a modified version of this program. Yeah. So we have, it's not what I wanted to show you, but this is demo. This is a demo, yeah, and it's not perfect. And so same stuff, but we also have a handler on issue closed that is registered for that event type issue closed. And what it does, it sends a signal to the workflow by its ID. Signal name is issue closed, and the payload can be anything. We don't actually care about the payload, but it can be any Starlark variable, like a dictionary or an array or whatever. And to construct the ID, we just extracted the ID construction into a function because we used it in two places. Now we deterministically assigned a name for the workflow that we start for a new issue based on the issue ID. And then we send the signal to the workflow identified by that ID. And here in the body of the workflow definition, we started using a signal channel. We listen for signals on the issue closed channel. This is the channel, and then we select on things in that dictionary. And this is only one thing here. As you see, that channel for the closed issue signal. And yeah, selected is whatever is selected, but only one thing can be selected. Also, we say we have a timeout for the select of 5 seconds. So every 5 seconds, this will be, if the issue is not closed, this will unblock, and it returns false if the timeout case is selected, basically. And in that case, we just pass, so do nothing, which triggers the next iteration of the while loop, which will run the code again. So we just kind of, as a fallback solution, we still want to check every 5 seconds. Not a fallback here. It's actually the business logic runs every 5 seconds as it was running before. But if the workflow was, sorry, if the issue was closed, then we must empty the channel we receive from it. We receive that issue was closed string. Actually, we don't need it, but we print it here, and we break. So we terminate that loop. We exit from the handler. So that should stop the child workflow that is running this handler. Okay, let's hope there are no typos here. Okay, let's open issue number 5. You can see it has applied the labels already. It works, and you can see it's running, but now it has a deterministic ID based on the issue ID. Now this is internal issue ID. So ID of the record in the database 504 is total number of issues created in this GitLab instance, not in project ID, but like global issue ID in that instance, because that's what we get in the event data. Yeah, it's running. Okay, let's close the issue and see if it. Yeah, see, issue was closed. Here the log is the log received. Issue was closed. Payload, and yeah, completed. Sorry, this one completed. And we can see that there should be timer canceled and workflow execution completed. Yeah. Oh, good, it works. So yeah, this is becoming more interesting, right? You can interact with the running workflow by sending signals to it, and signals can carry some payload, well, any data basically. And here, just a string, but it can be any structured data. So you can imagine external systems interacting with workflows using signals, or even GitLab as an external system to a workflow, which that's what is happening here. Okay, but this is basically polling, right? Every 5 seconds. That is not very efficient, you can say. So let's improve it. Let's make it run the logic when the issue is updated. So instead of checking every 5 seconds, we have the on issue updated event, and that also sends a signal to that same workflow by that same ID. So we have 3 handlers now. One starts the workflow, another one reacts to the issue closed event, and another one reacts to issue updated event. And as you see, we have it doesn't matter. We have maybe it does actually. It didn't work. If I I'll just remove all the spaces. So yeah, updated handler, updated binding handler to event. Then here we have the updated channel, select on the updated, and we added the updated case. And it doesn't do anything, so execution continues to the next iteration of the loop, which is what we want to check the issue for labels. Check the labels on the issue again. Commit, let's hope there are no typos. And let's issue number 6. Okay, labels are back. Oh, set. Labels are back immediately this time. Right. The added immediately, like there's no delay of 5 seconds. You see the execution starts immediately. And yeah, because timeout is 1 hour. So it will recheck everything every 1 hour if you don't update it. We can even remove this timeout if you want to, but I think it's good to have a mechanism to ensure that things are get into the desired state even if you have missed some event. Yeah, I think that's pretty good. You can't even remove both of them. It's faster than I can click. Anyway, and it should stop if I close the issue. Yeah, it's no longer reacting. And it's not gonna restart if I reopen because it's a separate event. That's not a new issue event. Cool. So yeah, we can send events, signals to a running workflow and react to things happening externally. We can block waiting for things that are happening externally. So imagine you can, that use case with deployments, you can start a deployment, you can pull it, but you can also just wait for it to call you back. And then you can proceed immediately. I think that's quite a powerful thing, right? Okay, but this always still kind of just a program that is executed periodically, that is executed on an event. But there's yet another big difference that I want to demonstrate, and I don't need to copy everything, I think. To copy only this function. Just trying to minimize the amount of things I need to fix. I wanted to minimize the amount of typing I do, but in the end. So here what we've done is we've introduced a variable. Everything is the same, but we have a variable that counts the number of times we have updated the labels. So yeah, on each time labels don't match, we increment it by 1. And if that reaches 5, we post a comment in the issue. Comments are called notes in the API. Okay, let's hope there are no typos. I'll close this one. Let's open a new one. Doesn't work. Create issue note is undefined. Yes, because I copied only what I needed. I also need the edit create issue note function from the library. This function just posts a comment, nothing else. But yeah, you can't post a comment without using that function. So, okay. This should be retried, I think. Yes. Just need to wait because there is an exponential backoff there in temporal. So yeah, the workflow execution has been scheduled. The activity execution to load the file has been scheduled. Activity failed. It finally retried again. The 7th something attempt was successful somewhere here. I don't know. Anyway, I think it works. One, so one is the first time it added labels. Second is the second time it added labels. Third, okay, let's stop it again. I just want to prove to you that it doesn't lose state. So labels are not added because it's the worker is not running. Let's start it again. Again, back off in temporal waits a while because worker is unavailable, but it should pick up the job in a second. So 1, 2, 3, 4, and number 5, it should post a comment. Yep. So yeah, it did post a comment. So state persists across worker restarts once again. I mean, imagine writing this as a shell script that persists program state. In this case, program state is just a counter. Yeah, it's trivial to persist in a file or something, but program state is all the variables everywhere in the program. And like, imagine writing all your abstractions and encapsulated data in a way so that you can persist it all and restore it all and restore where the program was actually executing. You cannot basically practically do this in a shell script or in normal code. You need some mechanism for that, and temporal is that mechanism basically. So this handlers are stateful. It's a program that basically you can think of it as it's running constantly. Doesn't matter if the worker crashes or whatever. So this is the end of the demo, but I also have other things I wanted to mention that I haven't demoed. So there are plenty of other features, queries. So I have demoed Signal. Signal is a way to asynchronously send data to a workflow. So you send data and eventually a workflow picks it up and does something or ignores or whatever. Then queries are a way to synchronously retrieve the data from a workflow. So you can have workflows that interact with each other, like send signals to each other and ask for data, like query. One workflow can query another workflow, or external system can query a workflow to see what's the state of those variables, for example, or anything. Then the updates are basically signals plus queries, so you can synchronously send data and receive data from a workflow. These are called updates for some reason. Then workflows can be started on schedule. That's probably pretty obvious what it does. And then this is the big thing, concurrency. So in a workflow, what I showed here is just a sequential program, but it doesn't have to be a sequential program. I haven't implemented that, but you can imagine that you can start multiple functions concurrently. So it's a matter of adding a tool to run functions concurrently to that W basically, or maybe a special syntax. Well, I can't add syntax, but I can add like global functions, basically like on event is a global function, predefined function. So like Go keyword in Go, for example, or I don't know, other keywords in other languages. So you can have Go, like in Go, you can have Go routines. Here you can also have an equivalent, basically streams of execution that are independent from each other within the same workflow. You can have separate workflows, child workflows, for example, of a single workflow, or you can have streams of executions within a single workflow. And then you can, for example, kick off, I don't know, several deployments that progress each one sequentially, but overall they progress concurrently. And then you can, for example, wait for all of them to finish, or wait for like 50% of them to finish, or whatever logic you want to implement, and then do something else. So concurrency is a thing here, even though it looks like Python that is single threaded, or it doesn't have to be this way at all. And if we go back to this slide, you can see that Starlark was designed for parallel evaluation and designed to be thread safe. But it's not thread safe because you cannot have concurrency. It's thread safe because shared data becomes immutable. So once you start a function, in that in the Starlark interpreter, there is a way to freeze global variables that a function refers to. So you basically cannot have mutable state that is shared by functions. But of course, you can pass parameters, you can pass something that where you could put data. So like in Go, you have channels. You can basically, we could use something like a channel here where you could publish the result of that concurrent execution. And then, or a future basically, or a promise, something like this, where you can pass values from one concurrently running thing to another concurrently running thing. When this finishes, or even dynamically, send values to each other. And once again, Starlark is a perfect fit here because of this property that everything can be frozen and you cannot have shared global mutable data, basically. So I didn't have time to implement support for concurrency, but it's totally a thing. Temporal also gives you various primitives apart from Go routines to synchronize concurrent Go routines. And they work deterministically. That's why Go, so this is the Go SDK that I use. So that's why they provide a replacement for channels, Go routines, other synchronization primitives, because workflow code has to be deterministic, must be deterministic. And those things are deterministic. So I think that's really powerful. Then other things that we could do, we could, as you saw, I was just editing the file and I committed it every time. We could design this to support local execution so that you don't have to commit it and test in production. And what's powerful is that workflow basically is a function that is fed events to reconstruct its state in memory. And then it interacts with everything by calling activities, which is like sending an event and receiving an event as a result of the activity. And if you replay events, workflow function will be in the exact same state. Then you can basically replay different streams of events to reconstruct different scenarios to get the program into a certain state and see how it will behave this way or that way, and assert that it behaves the correct way. So it's a perfect thing for unit testing, basically. And yeah, you can use actual production, or maybe not production, but production-like data, maybe obfuscated, to reconstruct the situations and run tests. And this can be done, or we could support it to be done locally. Well, testing, I already just talked about testing. Yeah, this is perfect for testing and for local execution. And we want to sell this, right? So what about the premium and ultimate features? So before I go in and talk about this, I need to show you this slide, this page. Temporal documentation is amazing, by the way. So detailed, everything is defined like in a dictionary, basically. And then you can yeah, it's really good anyway. So yeah, how does it handle the data? This is the temporal cluster or server. This is my client, and this is my worker that runs the workflow, and this is the worker that runs an activity. I have these two in the same program, but again, they can be different programs, and this can also be a different program. In my case, all three things are the same program, and I also have the server, the temporal server. And you can see this data converter here. So it's something that turns like a struct or an object in your program into a stream of bytes and back. And you can inject this into the SDK. So I'm using protobufs for payloads and results. And so this thing just serializes the protobuf into bytes. But it can also, and that's what they talk in the docs about, the payload converter. You can encrypt this, and temporal server actually doesn't see what data you are sending and receiving. So yeah, this is really great for security and for data is isolation, for multi-tenancy, right? Because each customer can have their own encryption key for their workflows, and then the data is pretty secure. If because of an error, some data is sent to a wrong client, it will not be able to decrypt it basically correctly. It will fail. And then here, this is what this feature is about. We could support bring your own key, which is often a very highly demanded feature by various banks and governments and other organizations that care about security and compliance. And yeah, we could add support for key management service providers. All clouds have these things. AWS KMS, Google Cloud, secret key management, Azure has the same thing, and probably all clouds have the same thing. And you probably have HashiCorp Vault, which probably also can do this. I don't know. Yeah, I think this can be an ultimate feature. Then you could imagine that people would want to automate business processes where humans are involved. So imagine a process where something requires legal approval. So the workflow can wait and create a UI with a button being a certain person, like assign to them something, or even maybe it can create an issue and assign to a person, and then that person needs to approve. Well, issue can be approved, but maybe an MR, or let's say if they close an issue with a certain comment that counts as an approval, or it can be a button, and the workflow can wait for this user to press this button, or press another button to decline, and workflow can take a different path and do something else, not deploy to production. For example, if SREs say no, this is not going to, you shall not pass, and it doesn't have to be a button. It can also be a text box or a drop down or anything other UI element where workflow can get some input from. I think this is also pretty powerful and can enable lots of business processes. And then, of course, this can drive adoption of existing features that we have. And as you saw, I have this personal access token encoded here, hard-coded, checked in, and that's obviously not good. Service accounts are a perfect fit here, right? Because you want to decouple automation from your human users, because if they move to a different group, they may lose permissions that the automation uses, and then it breaks. You don't want it to break, and you want to decouple it. So service accounts are a premium feature, and yeah, this is just perfect textbook example of where it should be used. And then, yeah, audit events and any other features, basically, we can integrate that. Anything that has an API can be invoked from the workflow. And the other way around, anything that can send a signal to a workflow can also kind of interact with it. And we have some OKRs to compete with GitHub, right? I'm not going to open them here, but let's look at the GitHub documentation. They already use the word workflow, but what they have is, I mean, it's not durable execution. It's just a sequence of jobs that passes data and automated process that runs jobs defined by YAML, checked in, triggered by an event in the repository, or can be triggered manually or run in schedule. That's pretty obvious. Workflow can also do this, but there is no durability in the execution, and it can't be that sophisticated, right? You cannot actually implement something like this in GitHub workflows. So, yeah, I think this, I mean, our sales folks could probably use this as a kind of as an argument to sell. Our workflows are kind of real workflows if we build this, and GitHub workflows are kind of a simplified version that doesn't actually cannot actually do what these things can do. I think, yeah, that's a pretty convincing argument, I think. So I think this can help with competing with GitHub. And really, if we want to one-up them, we have to offer something that's, you know, an order of magnitude or even more better than what they have. And I think this is what it is. And yeah, that's all I have. Thank you. I would also like to thank my teammate Tiger, who helped me with the Ruby part. Thank you, Tiger.